Hello, everyone. Welcome to the next section on our week 2 collection of tools for tectonics. The topic for this mini lecture is geomorphology. Now, geomorphology is not a tool, but a field, but it contains a number of tools which are extremely useful for trying to unravel tectonic processes. The reason for this is because tectonic processes have geomorphic expressions. These occur at really all scales, from field to continental. So for example, there are 3 examples here at different scales. This is the Tibetan Plateau, where the southern edge of the plateau along here is the Himalayan mountains. This is essentially a tectonic feature. This is created by the thickening of the crust or the lithosphere over this broad region. And at this scale, we can then try to analyze the morphology of this plateau in terms of those tectonic processes. Here in the middle is the Snake River. With behind it is the Teton Mountain Range in Wyoming. This is a tilted footwall of a normal fault that runs between the valley and the mountains. And there's been uplift of more than 2,000 meters in a relatively short period of time due to slip on this large normal fault. So by looking at the morphology of these mountains, we can say something about the distribution of slip and the magnitude of slip. Or at a smaller scale, you see a hill slope here on the island of Crete, where there is a distinct break or line along the lower slope of this hill slope. This is a fault. This is a fault scarp, where the upper part of the slope has moved up with respect to the lower part and exposed some of the bedrock along here. So this scarp is itself a geomorphic feature at the scale of meters to tens of meters that can tell us something about the slip rate on that fault. Now, much of geomorphology is involved with identifying markers. These are features of surfaces that can provide some kind of a reference to measure displacements of the Earth's surface. Those can be up or they can be horizontal, but they give us some measure of relative or even absolute deformation through their motion. For example, terraces represent a feature in the landscape. There are both marine and fluvial terraces. Marine terraces also have 2 types. They can be constructional terraces, which are formed from coral or other organisms primarily that are deposited at a specific elevation relative to sea level, so that if we find these say coral terraces at a different elevation, that tells us something about the vertical displacement. On the other hand, erosional terraces are formed by abrasional processes. For example, in the picture on the right, this is the wave action that is eroding the surface, leaving a relatively flat abrasion platform. There may be other features on the landscape. If it's eroding, for example, a wave-cut notch or even a sea cliff are all representative morphologies of this wave erosion. Now, as these sorts of features are uplifted into the landscape, they form very distinct geomorphologies. For example, here you can see a flight of terraces. Each one of these horizontal lines is a coral terrace. The fact that these are now found above sea level is evidence that this is a region that's tectonically active and uplifting these coral reefs. Erosional terraces are much the same. The problem being with erosional terraces that they essentially erode themselves. Right? They are transient features, and as long as the sea level is at a set elevation, you might form some features like this along the inner shoreline, but this will simply migrate in with time if the sea level is constant, and not be preserved, or be preserved only as a single feature. So it's important here that relative sea level change in order to permit these features to be preserved. Now, we're going to talk about this. We do talk about relative sea level because that is referring to the fact that the sea level might be changing eustatically, or it might be changing locally because of tectonic uplift or even tectonic subsidence. So it's always this relative sea level that's important. Now, the eustatic changes tend to be relatively cyclic. That is, we have high sea level, low sea level that's tracking with the ice ages and ice formation. So we have this sort of cyclic behavior of relative sea level on a coastline, and superimposed on that then might be some sort of a tectonic signal. If sea level falls rapidly, then it can leave stranded a marine terrace, for example, here, as the new one is formed here. If it moves too slowly, then it could be that things just sort of erode and migrate together. This raised terrace will, of course, then be destroyed the next time sea level rises back up to this level, unless there is some kind of tectonic process, say a background uplift rate, that is then going to raise that to the point the next sea level high will not destroy that. And we can see that nicely in a little model like this, where we can look at sea level impinging on some kind of a sloping surface and eroding a sort of a terrace or sea cliff as it encounters that slope, and just look at what happens if that sea level is following a curve like this. And this would be the typical sort of sea level curve. This could be a real one, but it is in some kind of a synthetic sea level history. But what you can see is that as the sea level goes up and down, it can leave behind a geomorphic feature, but as it comes back up again, that feature is very likely to be destroyed. So in fact, many of these little wiggles, the highs and lows, are not preserved in the sea cliff morphology here. On the other hand, it's about to hit right there a high. That high did not erase everything, did it? There are still features, for example, up here that were not completely wiped out by what was the highest sea level over this 350,000 years. And the reason these were not destroyed is because there's also a background uplift rate. This is the tectonic signal now, about 1 millimeter per year. And that means that in the time between the formation of these sea cliffs or terraces and this high stand, these features were raised up to the point that erosion could not, that high stand erosion could not reach those features. So if we can take this sort of a morphology, we can begin to interpret that in terms of these sorts of highs and lows in sea level and some kind of a tectonic uplift rate. But we have to keep in mind that this is not an accurate representation of every single feature in the sea level that may have happened. But the sort of typical suite of marine terraces might look something like this. These are a suite of marine terraces on the island of Crete. Each of these dashed lines represents a terrace. This is the average elevation of each of those terraces. So they're going up to 250 meters. So it's relatively high, right? And of course, like all of geology, we're really dependent on being able to absolute and relative date any of these sorts of features. If we can do that, then we can, and this is an example where there's a single age. This is an OSL, an optically stimulated luminescence age on gravels within that terrace. That yielded an age of 78,000 years. That was located on this lowest terrace right here. If we can date one or more of these terraces, then we can begin to try to establish a relative chronology, for example, by looking at the sea level curve, and that's what this is. This is the sea level curve, and relating each of these terraces to a particular high stand of sea level. So again, not all of the high stands are preserved, but those that are preserved, those that are high, and depending on then the background uplift rate, some of these will be preserved. And if we can then correlate these, and of course this is somewhat of an opinion, a subjective determination, but we can then begin to build this sort of a data set like this, where we can look at the current elevation and the age of each of those terraces, and from that we can back out an uplift rate. In this particular case, it shows a pretty constant background uplift rate, but with some kind of an acceleration towards the present day, at least apparent in the last 3 or 4 of these terraces. So this could in fact be interpreted as an acceleration in the tectonically driven uplift rate of this part of the coastline over this time frame. It's about the last 100,000 years. Geomorphic markers can also be used for horizontal motions. This is an example of a strike-slip fault, and you've probably all seen similar pictures where there's a strike-slip fault that's offset a river channel. That offset gives us a total displacement over some time frame. If something can be dated here, then we can use that to establish a slip rate on that fault. Other geomorphic or sedimentological features can also be studied, examined for this sort of offset and hopefully dated. This is an example of an alluvial fan in California, again, part of the San Andreas strike slip system. But you can see here the different features of the fan. If this fan's surface can be dated, then we can see the offset on the individual surfaces and establish a fault slip rate from that analysis. River terraces also make good markers. This is an example of a river terrace, which you can see in this picture is I think pretty clearly here. I'll show you a close up in a second. Is river gravels that are found in a deposit here, sitting on top of a bedrock, sort of a clay-rich bedrock along here. These are some meters to tens of meters above the modern riverbed. They did not get there from a flood. These were deposited order of tens of thousands of years ago. And in fact, this bedrock contact is the old riverbed. So if the river itself has stayed at a relatively constant elevation, which rivers often do because they tend to be sort of pinned to their base level, say at sea level or a sedimentary basin and further downstream, they tend to hold their elevation pretty efficiently, and the rock just sort of rises up through the erosional downcutting of that river. So this represents then the elevation of where this of where the river was, or more specifically, it represents the elevation the rock was when it was down here as the channel of this river. So we refer to this bedrock fluvial contact as the strath of a terrace. This is a close-up of that. You can see that this is in fact bedrock. This is a sedimentary bedrock. It was eroded by the river, and then river gravels were deposited on top of that. It's a type of unconformity. But in this case, this unconformity then is telling us something about the displacement of the rock relative to the river, which is way down here, over the time since that gravel was deposited. So if one goes into a river valley and maps out these terraces and tries to date them, again, dating is key to establishing absolute rates, but it's very common to find situations like this where we find entire flights of terraces. For example, here's a whole suite going from this green, blue down to yellow. Each of these, of course, is going to be older. The higher up you go, the older that terrace will be. And they are retaining then a record of the downcutting rate of the river, and we can relate the downcutting rate of the river to the uplift of the rock that's underneath it. Here's a little example of how that sort of thing might work. If we have a setting, like you look over on the right first, we have this is a thrust fault, the ramp of a large thrust fault that's uplifting here now the hanging wall over the footwall here. So we have a region of uplift. There's a river that's flowing across this structure. Here's the structure here. River is flowing across that structure. That river is down cutting. And again, the river may be staying absolutely fixed relative to sea level, but the rock is rising up through that incision of the river. As that rock rises, terraces form along the edge of the valley, and those terraces are uplifted by that rock uplift with time. So we come into a region like this and measure all of these terraces, map and measure and establish the elevations of these. We can reconstruct an uplift chronology, at least relative, and if we can date them, then it's absolute. And that can look something like this. So if you look at figure A on the left here, this is an elevation profile through a valley that looks very much like this. These are actual data from the Himalaya now. The modern river profile is this lowest line down here. Okay, so this is elevation distance. This is the river profile. And in this case, there are 3 suites of terraces with a common age found and mapped in this valley. And these are referred to then as T1, T2, T3. T is just terrace, oldest to youngest of these terraces. And the modern elevation is what these points are here. So that elevation, and you see first of all that there's both temporal but also spatial variation in the uplift. For example, T1 is hardly uplifted at all here relative to the points that are a little bit further upstream. And in fact, that uplift is decreasing as we fall back here now. Keep in mind also that the uplift is the difference between the elevation of the terrace and the river, not the elevation of the terrace and sea level or something like that. It's this delta, the difference here, that's important. If if we take that elevation difference and convert it to uplift rate by knowing, again, the age, and these are the ages of these terraces, 9,000 years, we find that, in fact, the uplift rate is pretty constant with time. Each of these terraces has more or less the same pattern of uplift, regardless of the age of that terrace. So they have the same temporal pattern and more or less the same spatial pattern, but that spatial pattern is not constant, right? This is not a region of constant uplift. In fact, it's almost zero here, very small at each end, maximum in the middle. Why is that? What determines this spatial pattern? Well, that's reflecting the ramp and the fold that is accompanying this ramp up in the near the front of this thrust fault. So in fact, this I can't quite reference it to this figure, but these terraces are all found right in here near the front of this thrust ramp system, and this represents higher uplift here associated with a fold as one comes up and over the top of the ramp right here. Okay, thank you for your attention.